now I'm going to introduce the algorithm that we developed based on using QRE model to predict how adversary is going to respond. Here is a brief introduction of a quantum response equilibrium. So QRE assumes that there will be error in the adversary's response. So instead of predicting a deterministic strategy of the player, QRE here is trying to predict a probability distribution over all the possible actions the player can take. So the probability, so in the security scenario, Qj here is the probability for the adversary to attack target J. And then this is going to be decided by the expected utility for the adversary if they attack a target J, given that X is the strategy played by the defender. And the denominator is just a normalized scalar. So here you can see that as the expected utility of attacking certain target increases, the probability for the adversary to select that target also increases. We have one lambda here, which is the parameter represents the error level in adversary's quantum response. So one extreme case you can imagine is if lambda equals to 0, then the adversary is going to pick any target uniformly with uniform distribution. And another extreme case is when lambda is very large, then the quantum response is going to converge to a best response. So in our work, we used maximum likelihood estimation to learn the value of lambda using the data we collected in experiment with human subjects. And the value we use in the work is 0.76. Okay. So if we model the adversary's behavior as a quantum response, then in order to compute the optimal strategy of the defender, what we need to do is essentially to solve this optimization problem. The objective function here is obviously nonlinear, and it's also in its most general form non-convex. Due to the non-convexity of the objective function, we focused on local search algorithms. So we developed BRQR, which is the algorithm to compute best response to quantum response. So we iteratively set the different starting point and Rong hill climbing to find the closest local optimal. So hopefully, as the iteration number increases, the probability of reaching the global optimum will also increase. So we have developed the algorithms based on the two proposed models. We would like to know how they perform with real human subjects. So we did experiment with the real human subjects. We first designed an online game. In this game, we're trying to simulate the security scenario at the LAX airport, where there are 8 terminals the police office need to protect. So we asked subjects to play as an attacker, and we asked them to select one target or one gate to attack. In this case, we tell them the reward if they successfully attack any of the target, as well as the penalty if they get caught by the police. We also tell them the probability they won't know which target. In this case, there are 3 guards, 3 police officers protecting 8 terminals. We will not tell them which 3 terminals are protected. Instead, we tell them the probability that the police office will be present at any of this terminal. And we ask them to choose one gate to attack. So we tested over 7 different payoff structures, including 3 from the previous work. And for each of the payoff structure, we computed defender strategy using the following 5 different methods. And PRBT and RPT are the 2 algorithms we developed based on the prospect theory, and the BRQR is the one based on QRE model. Again, Cobra is the leading contender in this field, and DOPS is the perfect rational baseline. So we asked each subject to play all the 35 games, and the order of the 35 games is randomized. Also, in order to mitigate the learning effect, we will not tell them the result until they finish all the 35 games. So let me show you the result here. So here what is shown here in this plot is the average defender utility in different payoffs using different strategies. So the higher the better. We can see here BRQR constantly outperformed Cobra and the Dobbs in all the payoffs. What is surprising here, BRPT has very poor performance. But once we incorporate the epsilon bounded rationality to modify the model, see the RPT has a significant improvement over BRPT. And also we can notice here is except for in payoff 1, where BRQR has slightly less performance, poor performance than RPT, in most of the cases, BRQR has the best performance among all the strategies. And this is the result in the 3 payoff structures that we borrowed from previous work, and we have similar patterns here. So let me just conclude. So as we expand the use of game theory to solve real-world security problems, it is very important to incorporate human behavior in the game's theoretical framework. And while we are trying to model the human behavior, it is also important to develop efficient algorithms to compute the defender's strategy. So in this work, we tried 2 different approaches by using prospect theory and a quantum response equilibrium to model the human behavior. And we also developed this efficient algorithm to compute defender's optimal strategy. And we did experiment with human subjects to justify the model. And then the result shows that BRQR, which is the algorithm based on using quantum response equilibrium, achieves the best performance in the experiment. So we are still in a very early stage of doing this work. There are a lot more work can be done. For example, we would like to explore human decision making using the data we have already collected. And also it would be interesting that to exploit the uncertainty in payoff structures. Dynamically adapting the model parameter would be also interesting. So, and some other things. And thank you for your attention. I would be happy to take any questions.
How do you figure out how to set the values of the different attacks to the attackers? So there are different values that the attacker gets for attacking door 1, 2, 3, and so on. How do you know those values?
Oh, you mean the payoff the game matrix? So in the experiment, what we did is we randomly sampled many payoff structures, and then we select some of them, because doing experiment with human subject is very expensive. We can't test all of them. So we selected some of them as a representative to test. So we actually run our clustering algorithm to cluster all the randomly selected payoff structures. And then we use the center of each cluster as a representative to be used in the experiment.
Very interesting study. You reported the results of the quality of the defender's policy based on the different theories. Did you also directly measure the predictive performance of the behavioral theories in your experiments?
You mean how different models predict the adversaries, the subject's behavior?
Yes.
We did have analysis on that. So QRE, I didn't show it here, but in the analysis result, QRE has the best prediction rate in terms of measuring their response.
Why do we believe that terrorists are going to have the same cognitive biases as lab subjects?
That's a very good question. I get that question a lot, actually. So it would be nice if we could really test this with real adversaries. But actually, this is a very common question to almost all the studies. I mean, involving experiment with human subject. Most of them are doing experiments with college students. But so at least here, what we can see is you see the BRQL, the best performance algorithm. One thing we could do is we could classify the subjects based on their cultural background or gender or some other information, and trying to get closer to the adversaries properties. There are some works trying to understand what would be the common personality or risk attitude of the adversaries. We could at least try to get close to the group, the special group that we really want to study. That's one thing. At the same time, even if we are not trying to take into consideration of the adversary's real attitude, QRE or the algorithm that performs best also the most robust algorithm to other kind of uncertainties in the games. So yeah, I'm not sure what I understood.